Not used to.
There we go.
I guess so.
Hi, everybody. Welcome to GAAC.
Yay!
Two speakers. Our own Mike Deneen is going to be showing us how to find M13 in the sky. And then we're going to have our guest speaker, Dr. Amy Williams from the University of Florida, who's going to give us a great talk that I look forward to. So first of all, here's Mike.
All right for me. Okay, I have to share my screen. This is going to be an adventure. And there we go. Yeah.
Excellent.
Okay. I got a little echo here. I'm not sure why. I'm muted. What we thought it would be nice to do is to have short, less than 5-minute presentations at the start of each meeting about how we do stuff in the sky. How do we find stuff? So we have a short series. I don't know how short it's going to be. We're going to run out of people. How I find blank. So this is how I find M13. It's one of the showpieces of the summer sky. So I thought we would do that. This will go by very quick. Here we go. You go outside and look what you're faced with. Where the heck is M13? How are you going to get around in the summer sky? Well, what you do is there's the summer Milky Way, and the brightest thing in the sky is right there. That's Vega. It's the brightest thing up there. Now, I know right to the east of Vega and the constellation Lyra, of which it is a part, is Cygnus. And the central star in the cross, which is lying on its side at about a 45-degree angle there, is Sauder. Okay? So, having found Sauder, you want a snack or something, so you walk slowly back to Vega, and not finding anything there. You keep going in the same direction for the same amount of time, and look where you wind up. There's Hercules. That's where M13 is. That's the keystone, the trapezoid there. We're pointing to. On the other side is actually where we've got to point our telescope. Now, how on earth am I going to point my telescope at that spot in the sky? That's crazy. It's going to take me all night. Is there anything I can get? Is there anybody that could help me? I used the Telrad. Here's one on a nice little telescope there. Here's another one on a less expensive but very nice telescope there. That's the switch on the side to turn it on. And here's one on a very nice telescope. You stand back here and look up through it. And what you see is the famous Telrad reticle. This is the target shape that's superimposed on the sky. Here, you're looking through a Telrad, and my guess is that's Jupiter, that little white spot in the bullseye. It could be a bright star, but my guess is it's Jupiter. That's what it often looks like. Here's another shot. That looks like the first quarter moon that they found in the bullseye. Okay? And here is Hercules, and that's M13 right there in a confusing vacant sky.
Oh, gosh.
And that's how you find M13. All right. Okay. Dr. Williams, I have to make you a co-host, so just give me a second.
No worries. That was a fabulous presentation.
Right up. All right. Share your screen at your leisure.
I'm working on it. You got it.
Eleanor, do you have anything to say?
I certainly do. I have heard Dr. Williams before. You're in for a treat. And please, if information that I give you now needs to be updated, Dr. Williams, please do so. Dr. Amy Williams is an assistant professor of geology at the University of Florida. She's an astrobiologist and geobiologist, and her research interests include the formation and preservation of physical and molecular biosignatures in terrestrial environments as an analog for putative biosignature formation on Mars. She's been a member of the NASA Curiosity rover science team since 2009 and currently works with the Sample Analysis at Mars, better known as SAM, at the Sample Analysis at Mars instrument team as a participating scientist to explore the distribution of organic molecules on Mars' surface. She's also a participating scientist on NASA's Perseverance rover mission and is collecting samples that can one day be returned to Earth. She received a 2021 University of Florida Research Promotion Initiative Award and the University of Florida Provost Excellence Award for assistant professors. She's also works towards increasing diversity, equity, and inclusion. I don't know if I'm allowed to say that.
I'm not allowed to say it anymore. That's fine.
Okay, so we'll just strike that from the record.
Oh, no, maybe you can say it. We'll see what they do, you know.
Well, I'm saying it. Okay, and that thrills me to no end. And she's also working on accessibility in the geosciences and STEM. Welcome.
Thank you so much. Thank you, Eleanor. Thank you, Michael. I am embarrassed to say that I had to look up to make sure I could pronounce the first word in GAAC, and I'm pretty sure it's Glaster.
Very good.
I did it? Okay, good.
Yeah.
All right. I am going to fly into Boston twice in the next 3 or 4 weeks, and that'll be the first time that I've been able to visit the area. So I'm excited to come up there, and sorry I can't be there in person, but I'm very excited to share with you some of the work that I've been able to do on Mars from my own desktop. And thank you, Eleanor, for inviting me quite a while ago after seeing a similar version of this talk. So I'm going to go ahead and jump into it, and hopefully this will respond. All right, awesome. So as you've heard, I work with 2 rover missions on Mars, and I like to call this talk, a decade of discoveries on Mars. But I found that you really have to go back, 5 decades to get the full sense for the exploration that we've done and that we hope to continue doing. And so let me just dive into that briefly here. So some of you may recall in the 60s to 70s, we were performing flyby missions, and we were sending things like the Mariner missions to take images of Mars. These were our first opportunities to get sort of that close-up look at Mars and to finally, truly acknowledge that there were no canals, the canali, that were thought to potentially be on Mars, remnants of some ancient civilization that was building canals to try to save themselves from their lack of water. And so in some ways, that destroyed sort of the image of Martians that we had in our minds from like H.G. Wells, and sort of that era of what would become science fiction. But we still had this dream of searching for life beyond Earth. Mars is a really great place to do sort of some of the experiments that you want to do to learn how to do this beyond Earth, maybe in other worlds. And so in the 70s, the Viking missions were sent. There were 2 Viking missions that had landers and orbiters alongside them. And Viking was sent in part to look for evidence of life on Mars. We did not find that evidence conclusively with those experiments, but we did start to learn a lot about why the red planet is what it is, why it is such an alien world that it turns out started out quite Earth-like. And so we only started to learn that as we sent orbiters and we were able to explore, wide swaths of the planet to be able to take images and see areas that look like they've been carved by water, even though there's clearly no water on Mars now. And so without finding evidence for life on Mars in the 70s, we had a bit of a hiatus in Mars exploration that was finally Mars exploration was restarted in 96 with the launch of the Pathfinder mission and the Sojourner rover. And you can see that on the far left of the image here. And so Sojourner was this little basically RC car sized robot. That was a technology demonstration to prove that we could drive a vehicle autonomously, or at least with a delay on Mars, tell it to do little bits of science and get something back from that. And so it was a resounding success. Sojourner could rove around and had a little instrument on the front of it, so kind of boop up to a rock and get some elemental analysis of the rock. And this is just, a game changer in our ability to explore a world where we couldn't, and we still can't quite yet, send people. So the next logical step in that was sending more rovers, and we sent more and more robust roving vehicles. So the next iteration were the Mars exploration rovers, Spirit and Opportunity, which launched in 2003. And so beyond that technology demonstration, now we can start to ask real questions about Mars. So these rovers were meant to follow the water and look for evidence of extensive water alteration, evidence for lakes, rivers, you have it on Mars. And they actually found that in great quantities. So we know that there was a lot of water on Mars in the past, and it's been gone for quite a while now. The Phoenix lander landed near the North Pole and actually found our first evidence for water ice by scooping into the subsurface just a little bit and revealing water ice that sublimated within a couple of hours to a Martian day. So subsequent to that, we have the Curiosity rover that launched in 2011, and I'm going to get to talk more about that given the experience that I've had working on the mission thus far. Building on Follow the Water, Curiosity was built to follow the carbon and look for evidence of organic carbon, which, as I'm sure you all know, is what we all are made of. Life as we know it is made of organic carbon. And it's also generated abiotically or without life on meteorites, which can then rain down on these planetary surfaces. So we have, in fact, found organic carbon, and I'll get to talk a little bit more about that. I know Michael sent that out in the advertisement email, which was very kind. So moving forward from there, let me skip over to the Mars 2020 Perseverance rover. So we've gone from follow the water to follow the carbon to search for signs of ancient life. So the Perseverance rover is currently exploring an area where we are collecting samples that we would hope we can one day return to Earth to be able to use the full suite of instruments that we have on Earth to interrogate these samples to try to learn if, that most profound question of whether we're alone in the universe, perhaps we can find it just in our next door neighbor here. So with that, let me jump forward and I want to spend a little bit of time giving you a tour of the work that the Curiosity mission has accomplished so far. And so let me just jump in here to our spec sheet for the Curiosity mission. So this is the Curiosity rover on the right. This is in front of an area called Mount Mercou. Curiosity was supposed to only operate for one Mars year, which is about 2 Earth years. And we are currently more than 6 Mars years or 12 Earth years into this mission. I just updated this today. We are on Sol, or Martian Day, 4,505. We have driven more than 21 miles or 34 kilometers. And so what I want to do is tell you a little bit about where we went with this rover and why we went to the place that we did. So let's go down to this map. So this is a map that uses laser altimetry to tell us how high the elevation of the land surface is. And so the reds are high up, the blues are down low. And we're going to go to the Martian dichotomy here at Jezero Crater. So we'll zoom in on Gale. So Jezero Crater is a 150-kilometer wide impact structure with a 5-kilometer tall mound of sediments in the center. And let's get a little bit of a higher resolution image here. So the rocks that are in that mountain called Aeolus Mons, were really intriguing to us because they record evidence for a dramatic shift in the Martian climate from one where there was abundant water in the ancient past to a far drier climate more similar to what we see today. And so the superposed image that you see here is where water actually flowed from the crater rim in a river down onto the crater floor. And that blue is colored in to show you sort of where a lake would be in Gale Crater. And so these were some of the reasons we were so excited to explore Gale. And so let me tell you a little bit about how you get a mission like this to Gale Crater. So, with the Mars exploration rovers, they were small enough that we were able to use basically airbags to land them. And so you would, come down to Mars and you would bounce and you would, go really high up in the air and bounce again until you finally lost your momentum and settled, and that's where the rovers would land. You couldn't do that with Curiosity because it just weighed too much, and we had very little precision where our landing sites were with the MER rovers with that technique. With Curiosity, what we developed was something called the sky crane, which is like basically putting a rocket pack on the back of your rover. So instead of airbags, we use these rockets to slow ourselves down as we approach the Martian surface, drop the rover down on a bridle from there, as you see in the animation. And then once you touch down, the sky crane is meant to fly away, crash land somewhere else, not smash your rover. As you can imagine, it's really hard to do this start to finish testing on Earth, right? We don't have the same atmospheric density. We don't have similar conditions that would enable you to perform this end to end. And so the first time that we saw this work was when we landed on Mars. And so as you can see, there's great excitement from our engineering team that this was able to actually work. You can land a roving geochemistry lab with this technique. And so what I want to do is just in one slide, basically summarize what we've discovered in the past 12 years. So the first and biggest thing is that there's evidence for persistent liquid water in Gale Crater. And this just corresponds with what we've seen with other missions, with the MER missions, which landed in 2 different locations as well. And so one of the really cool things about this is that one of the first rocks we saw when we landed was it had evidence for water in it. And so if you look at these images, the image on the left is the picture of the rock we landed on Mars. And actually, those rockets from the sky crane blew the dust away so that you can see the underlying bedrock. This type of rock is called a conglomerate. It's a rock made up of big chunks of other rocks. It's a sedimentary rock, and it forms when you have water that flows fast enough to carry grains of that size. And there's a scale bar on here so you can see how large those grains actually are, little pebbles, really. The image on the right is showing you just an example of a conglomerate with similar grain sizes. And so what's really cool about this as a geologist, what I can say when I see grains of this size is that, we know that the river that carried that water, that carried those rocks in the water, was probably ankle to knee deep. So this is no tiny trickle. This is an actual river. So you can almost picture Mars in this very terrestrial way with something that you may have seen at some point in your own lived experience. So that's just like starting a mission that way is just a fabulous way to set the right tone. We've also found suitable evidence or suitable environments for microbial life if it ever existed on Mars in almost every drill hole that we've made. So I think we're on drill hole 42 at this point. And in almost every one of these, what we see is basically a way that at least microbial life on Earth could use the minerals that are present in that rock to eke out a little existence, a little bit of metabolism. You can really see it well illustrated in the images where you see the bedrock is red and the drill finds are gray. One of the more extraordinary things that we discovered early on is that the red planet is only millimeters thick. Once you drill down into the subsurface, and these drill holes are at most 6 centimeters, you get into a whole nother world that was just slightly shielded from us, that we couldn't really explore that before we were able to drill into the subsurface. We've also found evidence for organic carbon preserved in many of the Martian rocks that we have explored. So again, organic carbon doesn't necessarily mean evidence for life. It's made in the interstellar space, it rains down on planetary bodies as meteorites or interplanetary dust particles. But detecting it can tell you something about the building blocks for life as we know it, what's present on these worlds, what was present in the ancient past that might have led to an origin of life on another world besides Earth. And so we've had a lot of great success with this with the SAM instrument, which Eleanor kindly mentioned that I work with. We've also learned a lot about how methane functions in Mars's atmosphere. And we've also learned that we don't know kind of key things about how methane functions in Mars's atmosphere. So methane is considered one of these gases that some folks have speculated it could be a biosignature, it could be evidence for microbial life because it should break down extremely quickly. We see these plumes of methane once in a while, and the way that they appear and dissipate, it's not really performing, it's not or existing the way that we expect it to. It's almost as if there are these episodic releases. We've been trying to understand where that comes from and how sort of these boundary layers within like the planetary atmosphere actually influence kind of the release of this methane, if it's geologic, if, could it possibly be biologic? In my view, until you have way more evidence for life, you don't make that call until you have multiple lines of evidence that come together. But it does mean that there's just so much about Mars that we haven't learned yet. There's still so much to learn. These missions also help us characterize the radiation risks for humans to Mars. So with an intention to eventually send humans to Mars, which has been an intention for decades before now, understanding the environment and what kind of challenges our astronauts would face is one of the key things that these missions can do for long-term exploration. And then finally, we have this evidence for a thicker atmosphere and more water in Mars's past. And so one of my favorite things to show, and if your room is really light, it may be difficult to see this, but this is just like 4 images stitched together of these clouds passing over the mountain. And, as a geologist, I've spent a lot of time out in the desert looking at rocks with little plant matter on it. And as the sun sets and the clouds are passing over the mountains, I could be on Earth watching this, but this is happening on Mars. And so it's, again, one of those things that really gives you this feels like this humanistic tie to another world that I know personally I'm never going to go visit. But it gives you a way of thinking about how these worlds evolved, how they began so similarly, and how their planetary evolution has led them apart in such interesting ways. So, that's my best effort to summarize 12 years of science. There's so much I could go into, but let me tell you a little bit about what's coming up ahead of us. So this is one of my favorite images of the upper mound of Gale Crater, and we took this when we were way, way, way back down on the crater floor. The blue sky that you see here is not the real color, of course. The real sky is sort of this like salmony color. But it turns out that if you color adjust and make the sky blue, especially for geologists, our eyes are able to pick out details in the rocks that it's actually really challenging to see with like the Martian atmospheric color. So this makes this, again, almost look terrestrial, but this is on Mars. And what's really fabulous to me is like we are way up in one of these upper areas above this marker band. And we've been traveling for 12 years to get up here and just learning so much as we've been making this ascent up these layers. Because, as a geologist, what you can do is sort of read the layers of sediment in this mountain, sort of like pages in a book in the history of Mars. And it's one of the really incredible things about, having the skill set on Earth and applying it to another world, because I feel like I can really just see this transition from this wet environment with lakes and rivers, and you see this desiccation occur. And so let me show you actually where that transition happens. We got up onto Mount Sharp. We crossed over what's called the Vera Rubin Ridge here, which is, you see, we kind of spin around in circles for a bit. We're actually getting our drill back online. It went offline for a while. We re-engineered how we drilled, and we were actually able to collect more samples that give us way more insight into, one of the things I focused on was the presence of organic carbon. And so we saw so much more organic carbon preserved in this green layer called the clay-bearing unit. The clay-bearing unit tells us that it was laid down in an environment where there was a lot of water. That's where you get clays forming from aqueous alteration. And we go through this transition up into the sulfate-bearing unit, which is yellow on this map. And that tells us that we've now transitioned into a drier environment. There's that episodic waters. I mean, it really is episodic at this point, and you just have these little pulses of water. We see things like wave ripples here and there, but you're seeing a lot more things that look like sand dunes. As we're climbing up the mountain. And so you're seeing this at least regional climatic shift that may even have something to do with the more global climatic shift that Mars experiences. It became the cold, dry desert that we know today. So, one of the cool things is from orbit, you can tell there's a major environmental transition on Mars, and then you can send a rover and get, wheels on the ground and get way more insight into the details, the nuance of that environmental transition, and really insight into a world that is sort of paused in its infancy for us. So the exploration and ascent of Aeolus Mons, or what we informally call Mount Sharp, continues. And so let me back away from Curiosity and take you to the other flagship mission that's currently operating on Mars, which is NASA's Perseverance rover. So this is Percy. A couple of mission specs to share with you on this mission. So we are 1,472 sols into this mission. We just passed our prime mission of 1.5 Mars years, and we are rapidly catching up with Curiosity. We've driven almost 21 miles, so we will surpass Curiosity here very soon. You'll notice here that there's a helicopter log. We actually, for quite a while, had a helicopter tagging along with us called Ingenuity. She was the first, another technology demonstration, just like Sojourner was, demonstrating powered controlled flight on another planetary surface for the first time. And one of the really cool things, like at this mission, or that tech demo aspect was supposed to fly, I think 7 flights, and we flew 72 times. So it was wildly successful. And one of the really cool things about that tech demo is actually that mission carried a little piece of the Wright brothers' original airplane, a little cloth square. So we took the first, human-powered flight on Earth and sent it to the first human-powered flight on Mars, which is just this incredible connection with exploration and human ingenuity. So the other thing that's different on this spec list relative to Curiosity is listing samples and cores. So as I mentioned before, Perseverance is collecting samples from carefully characterized environments in a place called Jezero Crater with the intent that those samples could be returned one day to Earth. And I'll get to talk a little bit more about that in a bit. So let me tell you a bit about the site that we went to explore here. So we're going to the Martian dichotomy again between the southern highlands and the northern lowlands, a little bit further to the west on this map than GAAC Crater, to a place called Jezero Crater. So here's Jezero. It's just a 50-kilometer wide impact crater, and you don't see a central mound. You actually see it's pretty flat, and there's this really interesting structure on the western flank here. And so we can zoom into this and get a higher resolution image. This structure is like, you can't build it anyway without water having something to do with it. So this is a feature commonly called a delta or a fan, where you have water that was pouring out from that left-hand channel and pouring out into the basin. In some of the characteristics of the fan, it actually indicates that river was pouring into a lake. And so even though Jezero Crater currently looks like you're seeing it here, in the past, we believed it looked more like a water-filled crater lake with an inlet, and there's even an outlet channel on the far, would that be southeast side. So you have this really dynamic system in the ancient past. And so we wanted to explore this to look for rocks that could tell us whether there was evidence of life in this environment in the ancient past. So let me tell you a little bit about landing there and our exploration. So we first landed on the crater floor. We again used the sky crane system. And so one of the cool things that we've done with these missions is name our landing sites after science fiction authors. So this one is the Octavia E. Butler landing site. With Curiosity, it was the Bradbury landing site. So let me zoom into our landing site here. You can see this up at the northern extent or topmost part of my slide here. And we actually, instead of going towards the delta immediately, went to the south and kind of bopped around in this area because we were trying to understand what kind of rocks were we in. We expected if there was a river flowing into a lake to be on lake sediments. And so we were trying to understand what we were looking at. And so we drove around and we're taking images like I'm showing you here, flat pavers, sort of flat lying stacked rocks. It it wasn't really jiving with what we expected to see. And so it wasn't until we got down into this lower section here, you see named Seta, that we saw these types of crystals of a specific mineral called olivine in the rocks. And we came to finally accept and stop arguing amongst ourselves that we had actually landed on the volcanic or igneous rock basement of this crater floor. So likely what happened is that there were lake sediments at some point, and you've had 4 to 3.5 billion years of erosion, winnowing away those really fine sediments and lofting them off into the wind and depositing them somewhere in the northern hemisphere. So although we lost those lake sediments, we actually get really incredible insight into the basement rocks, which helps us actually constrain how old the crater is and how old that delta is, which tells us when water was flowing on Mars. Now, of course, we can't perform those experiments with this rover. These samples actually need to be returned to Earth to perform those precision absolute age calculations to determine exactly how old those rocks are. But we got cores from this site in the crater floor, and we actually got them in doubles because we depoted 10 of them at sort of a triage site in case the rover falls off a cliff somewhere. Then at least we have 10 samples that would be worth returning. So from the crater floor, we turned towards the delta structure, that fan structure that I had mentioned. And again, remember, we're going there because river deltas and fans are habitable environments on Earth. So that would be a place that we would want to look for evidence for life preserved in the rocks on Mars. And if you look at the fan or the delta from orbit and you look at the minerals that are present in there from some of the instruments on our orbiters, we actually know that a type of clay called smectite is present in the fan, and it's really ideal for preserving organic carbon. So as you've heard before, that's one of the things that I really care about in the search for life beyond Earth. And so we wanted to explore these types of rocks and hopefully find that evidence. So we made a beeline around Seta over to the delta front to collect a few more samples from this delta region. And so let's zoom in here. I'm going to give you sort of a pause point of where we were in our delta exploration. We came in, excuse me, along the crater floor. We went to the south to explore sort of the contact between the crater floor and the delta front. We ended up going up north in part to characterize this area because it ended up being where we depoted our samples, and we had to take a lot of images for that part of our work. We explored this part of the delta, went back through, grabbed a couple more samples, depoted, and we actually continued our traverse up the fan to the north here. But let me show you some of the cool things we were able to explore when we finally got to our first sedimentary rocks. As we drive around, we actually had the opportunity to look at this beautiful delta remnant. This is one of my favorite images from this mission, I think. We call this Kodiak. We give names based on these quadrangles that have assignments for example, different national parks from the US or different areas around the world that have low populations, geologic, they're special to geologists. And so that's where these names come from. And this particular delta remnant tells us that there was water in a river flowing down into a lake and forming a delta the way that the geometry of these rocks is laid out. And so it was just more confirmation that you have this aqueous environment interacting with the crater floor in the ancient past. We finally get up to the base of the delta, finally see our first sedimentary rocks after, an Earth year of working our way around the crater floor. Finding actually some of those fine-grained rocks that might actually hold evidence for those organic molecules. So we sampled our first sedimentary rocks here at the delta front. And so what I wanted to share with you is sort of a collage that has both the crater floor samples as well as our first sedimentary rocks from the delta front. So you can see most of these are collected in doublets because we depoted them down here in a place called Three Forks, right at the base of the delta. So, I'm going to end up having to skip like so much of the science just because there's so much more that we've been able to explore. So let me just back all the way out and take you to the ultimate goal of this entire project. And that is to collect samples going all the way up from the crater floor through the delta, where if there was life, it's like very likely to have been preserved in the rocks there and still be detectable today with instruments that we have on Earth. We went up and over the fan, over the crater rim, and we are actually out here. We're actually further along even than you're seeing from this image, in what's called Noachian basement. So the Noachian is basically the earliest time on Mars where there was likely water. The pre-Noachian is sort of like our Hadean. It's just really like Hadean, is like for Hades, right? It's really hell on Earth. So that would have been hell on Mars. And so we are out here in basically the oldest terrain that any rover has explored, able to collect rock samples. And I love this family portrait of all of our samples, what we've depoted at Three Forks on the right-hand side here, and then our onboard cache, including rocks, atmospheric samples, and regolith, to give us sort of this insight into Mars as a world as we can see it through Jezero Crater in a way that we've never been able to explore before. And this all feeds into Mars sample return, the ability to get Mars rocks back to Earth for the first time when they aren't ejected as meteorites and floating around in the solar system, to be able to bring them back to Earth from carefully selected locations in Jezero, and to be able to ask these most profound questions about how Earth and Mars started similarly and evolved so very differently, whether there was ever life on Mars preserved in those rocks. When was water flowing on Mars? I mean, it's going to give us constraints that we simply cannot get any other way. I'm just about at the end of the presentation here, and I'll just pause to say that today was a really disappointing day for me because the president's budget request came out and it cancels Mars sample return, and it cancels a lot of the extended missions, including probably Curiosity. So my entire career is probably going to be canceled. And it's really disappointing to see that in planetary science. I know that astrophysics is facing a 70% cut. The Nancy Roman telescope will be cut. There's so much on the line, and I try to never make these talks political. I want them to be inspirational, but this is really my only way to reach out and say, if you care about preserving this kind of science, planetary science, heliophysics, astrophysics, really any science, consider reaching out to your elected representatives and telling them that you care about this and that you want to see it supported. And so that's not normally what I would say in this talk, but it's been a really tough day, and I wanted to share that all with you. And so let me leave you with something hopefully a little more inspirational to you. That we've had these decades to explore one of our nearest neighbors, that we've learned so much about a world that evolved so differently from us. And let me just leave you with one of my favorite quotes as an astrobiologist, and just as a human, that the universe is a pretty big place. And if it's just us, it seems like an awful waste of space. So with that, thank you so much for listening in, letting me rant for a little bit. I truly appreciate it. And I would love to take questions and have a conversation with you all this evening. Thank you.
Thank you.
Thank you, Dr. Williams.
So I'm going to stop sharing my screen if that's okay, and then I can see you all with questions, if that is all right. Let me stop sharing real quick. And then, so Mario, I see your hand online here, and then I don't know, Michael, if you want to control questions in the room, if there are any. But Mario, please go ahead.
Sure. Great presentation. I really enjoyed it. In so much a question as empathy. I share your concerns as a physician. I am horrified at what's happening to public health, and horrified at the people who were put in charge of health, and the cuts there are just as atrocious. So I'll leave it at that, but I share your concerns.
Thank you so much. Alan, I see your hand up.
Thank you very much for this great presentation. I was actually thinking as we were watching you carry us through all this stuff, I wonder how much longer you and other people will be able to do this work. So again, I share with you there, and my elected officials will also be hearing from me. I had two basic questions. You mentioned how much longer curiosity has lasted compared to what we thought or said it would, and all of our missions just seem to go on so much longer than we say. Is that because we chronically underpromise, or is it because we're really surprised at how robust our hardware and software and planning and everything else is?
Yeah, let me answer that question for sure. So you remember how I was pointing out that we went to look for life on Mars with Viking, and then we had a 20-year hiatus? One of the lessons learned is you better be able to deliver what you say you're going to do. And so, you'll notice that like you know, finding evidence for water, right? We were pretty sure there was water on Mars in the past. But what we found wasn't just, oh yeah, confirmation, done, right? It was a whole, you can tell about the types of water, you can learn about the hydrologic cycle. I mean, there's so much to get into besides just there was water. The same with searching for organic carbon, and hopefully in the search for evidence of life beyond Earth in these ancient rocks. So now what we do is you want to make sure in your prime mission you can accomplish your goals. Um, and we do lifetime testing that, give us confidence that you can go multiple lifetimes beyond the first point of failure. Um, Things do fail. Like I said, like we bopped around in Vera Rubin Ridge for a while trying to get the drill working with Curiosity. And that was actually a huge undertaking of figuring out, instead of, we had the drill that would extend out, and that failed. And so what we did was we just left it extended. And instead of using our stabilizers to try to, if you're drilling into the wall, you might stabilize yourself. We didn't have that. We had to develop a brand new way to drill, that we weren't expecting to have to do, right? But it enabled science that would have been lost, more than half of the mission. So it's not under deliver, or not under delivering, but under promising. We are meeting our lifetime goals and our prime missions. But man, the science that you get out of extended missions is incredible. And so if you think about the Opportunity rover, that was one of the Mars exploration rovers. Those two were meant to go for 3 months. They were solar powered. And because Opportunity was able to tilt in such a way, and it was also in a good place where there was a lot of wind activity and dust devils, it was able to keep having its solar panels cleaned, and it went for 14 years. So some of it's fortuitous and serendipity, but some of it is just really good engineering. And I would say a perseverance to push through when you find those challenges and find a way around them. That's
Thank
an
you.
excellent question. Thank you so much.
Great answer. And my other question is, how much
Oh, yeah.
geologic time does that drill, those several centimeter drill holes actually cover, and how deep does the red go?
So that's a great question. It depends on the area. As a geologist, I can tell you if you go through a contact, you can go through millions to billions of years, depending on what you've drilled through. Many of the rocks that we're dealing with, again, we don't have absolute ages, but just in general, I mean, you're probably looking at hundreds to maybe thousands of years in an individual, like drill hole. But over the course of, like with Jezero, because it's a smaller crater and we'd be able to climb out, I mean, we're probably looking at a billion years of time, which is pretty cool.
Thanks, and thanks for your service.
Thank you so much, Alan.
But I have a question here in the room I want to jump to.
Please.
Right here. Oh, there you go.
Hi.
Hi.
Yes, thanks for the talk. Fantastic talk. It seems that there was a lot of water on the surface of Mars in the past, and I just wonder where the water is today. Is it in the atmosphere? Is it in the subsurface? Do we know or don't we know?
Great question. Something that we've all been working on. So a lot of the water was lost, not even just to the atmosphere, but when the geodynamo that creates the magnetic field around a planet, failed on Mars. Mars is a third the size of Earth, so that rotation of the core, slowed down and failed. Then you don't have a magnetic field, and you don't have a way to protect the planet from solar winds. And so those solar winds winnowed away the atmosphere. With less atmosphere, you have lower atmospheric density, and you move away from the triple point for water stability. So you either have a little bit of water vapor or a lot of water ice. And that's probably where much of the water was probably lost. What is still there is water ice in the subsurface, is a lot more at the poles. And if you go deep enough at the equator, you'll still run into some. And then there's been some recent studies that have suggested that some of the water is actually locked up mineralogically. So basically, like waters of hydration that are part of mineral structures in the subsurface as well. So liquid water is really not stable on the surface today in sort of the orbit that Mars is in right now in its like climatic period. But it has been in the past, and there are periods when it probably will be in the future for limited periods of time. But some of that water, of course, was lost as the magnetic field was lost in the atmosphere winnowed away. Great question. Thank you. So I know I saw a hand earlier online here. Phil. Yeah. Oh, you're muted, Phil. I just did that today on a call.
My question dovetails with the prior question, which is, it's exciting to know that there is subsurface ice on Mars. My question is it toxic or is it clean?
Well, it depends on how you define toxic, right? There are
I mean, could we
organisms.
drink it? I guess that's,
Oh,
yeah.
okay. So my point was going to be there are organisms that live inside of nuclear reactor water. So toxic is a relative term for
Yeah.
microbes. So the water that's on Mars in ice form is almost certainly very briny because you do dry out the environment. You have salts precipitating. And so that seems to be a pretty widespread phenomenon on Mars. And so almost certainly most of that water is briny and would have to be basically desaled before it is potable. So even if you send humans with the intent of harvesting water ice, there's processing that would have to occur.
And then the second follow-up is, how would we generate oxygen for humans to breathe on Mars? Would it have to come from water ice, or is there some mineral process that we could extract it through chemical reaction?
So there's been discussions about using water ice to actually feed into propellant, like rocket propellant. There was an experiment on Perseverance called MOXIE that actually generated oxygen from the CO2 atmosphere. So there are these little tests to see how you might be able to do that. But for the first humans to Mars, it's going to be bringing oxygen and recycling oxygen in their habitats or within their vehicles. Yeah, good question. Was there another one in the room before I go back to Mario? And then, Eleanor, I see your hand now. Sorry.
The room, you want to speak? Anybody in the room? Well, I thank you very much for speaking to us, especially at this difficult time. I think most of us will be contacting our legislators. I think action is an antidote to despair. So thinking about the generations that have grown up being excited about space exploration, it is really quite devastating. Needless to say, we will follow up.
I really appreciate that, and I'll just leave it as a positive that I'm turning 40 this year, and so I know that there are parts of our even recent history as a nation and as a world that I haven't experienced and have probably felt similarly devastating in different ways. And so I try to keep that perspective that we have come through those things. I intend to come through this, and to hopefully be a beacon for all of those early career scientists who struggle through this time and then can come through again. This isn't the end of science.
And
We
you
won't
can't
let it be.
squash human curiosity. You just
That's right.
can't. You it
That's
will.
right.
I wanted to ask you about the little blueberries on Mars.
Yeah, yeah.
Right? Do they, in studying those, do they see any evidence of the water being there in the past, either in the formation of these little blueberries?
Yeah,
Or
yeah, absolutely. Yeah, so those features are actually one of the things that gave us evidence that there was water interacting with the basically the bedrock. You actually see these in Utah, and so you have water passing through the rock, and it facilitates oxidation reduction fronts that help these little blueberries to form. And so they start as a little nucleus and they grow out, and so that's where you see them as these spheres. Yeah, they're just chemical reactions, but they are driven by water. And so seeing those actually was one of the things.
Mm.
I don't remember if I thought it was Spirit, but maybe it was Opportunity. I don't remember which rover now discovered them, but that was like, oh my gosh, like you make these with water. That's incredible. So yes.
And how long will those samples remain if we're not going to pick them up immediately? How
I
long?
mean, they've been there for billions of years. They'll be fine in the tubes.
The tubes, that's what I was wondering about.
Yep, they're inside the tubes. Where the 10 samples are depoted, the sand doesn't move very much. So if it takes longer, if some other nation decides to return them for us, they'll be fine. They'll be fine. Yeah. I saw a few more hands, but I don't know how late you all wish to push this. So I leave it up to Eleanor, Michael, whoever. If there's time for a few more questions, I'm happy to take them.
Mario's been very patient. Mario?
Yeah, Mario, please.
Yeah, thank you, Amy. So, a few years back, a meteorite sample was found that was felt to come from Mars. And
I know where
in
this
the
is going.
yeah, okay. In the sample, there were things that superficially at least look like microbes. So first part of the question is, what are your thoughts on that? And two, if you get the samples back from Mars and that's what we see, what will it take to say there once was life on Mars? What are you looking for that's different from that?
Oh, that's so great. And I do get that question a lot, so I do appreciate it. So what Mario is referencing is the Allen Hills 84001 meteorite. So this is the work by McKay and others starting in 1996. And I will pause to say that the astrobiology program at NASA would not exist without what happened, which is that Dave McKay and colleagues found these little nanoscale, turns out, features within the meteorite and a couple of other lines of geochemical evidence that they said alone maybe wouldn't indicate anything biologic, but together they said that they can't say that it's not evidence for life in that meteorite. They sparked astrobiology, the program, to actually become a real thing. As an astrobiologist, I'll say that that was not evidence for life in a Martian meteorite. There's a bunch of lines of evidence against what they were pulling together as these lines. One of them being that there's no organism known on Earth that could possibly hold any kind of reproductive geochemical molecules. So basically DNA, RNA, the smallest possible thing. You can't fit it into the size that that organism would have had to have been because it was truly like nanometers. So that's not evidence for life. I believe Dave McKay passed believing that he had found evidence for life. So I think it's a really important lesson for all of the astrobiologists. If you claim life, you can't step back from that. And so I approach all of this a priori that there's not life on Mars, so that I have to be very strongly convinced by multiple lines of converging evidence that there would be life. So if samples, we return samples, you have an appropriate environmental context, you have complex organic matter that we don't know any way you could make that abiotically. if you find physical features that may look like what I'll describe as life as we know it, so cellular, then I think you're onto something that you can start to form an argument about. We will argue forever if we think we found life in those return samples, I feel.
So complex carbon sediments would be what you're looking for.
So yeah, and certainly my response is biased by my expertise, right? So like chlorophyll in plants and also bacteria, it's the molecule that facilitates photosynthesis, right? There's no way that we know that abiotically something like that can form. So seeing that, I'm not saying that that's what we would find for another variety of reasons, but if you picture something that complex, that requires biosynthesis as we know it. So that's what I would be looking for. Really awesome question. Thank you.
Do I have time for one? Quick one?
Michael, is there time?
For one quick one?
Yeah.
I can't hear what he's saying, so I'll just ask.
I say go ahead. Yeah.
If the worst case scenario does happen to you in your program and it gets squashed in a subsequent administration, would that just turn back on again, or would we literally be back to zero, have to get new funding and start all over again? That's my question.
There would probably be a lot of starting over from zero in the sense of both funding and restarting programs, leaving things on the ground. You have to fix those things once you've let, it's like leaving your car sitting for a while.
Mm-hmm.
And also one of my concerns is the number of scientists and engineers who will leave the field entirely. In recovering. I mean, it's a brain drain. And I already have one of my students had his grad school offer rescinded because we can't, a lot of places aren't able to confirm funding. We don't know what's coming. And he is brilliant and I am heartbroken for him. So,
Well,
yeah.
Hopefully it won't come to that. And then with the drill holes, how deep does the red go? Because I noticed
Oh,
the
yes.
stuff coming
Yeah.
up was gray.
Well, yeah. So that's what it is. Sometimes it's red all the way down if you have a really strong oxidation front, but sometimes it truly is millimeters. And then you get into the gray. Yeah. So that's what I said. The red planet, it's only skin deep.
Yep, that's what you said.
It's pretty
All
cool.
right, thank you.
Yes.
Great presentation.
Thanks.
Okay, Amy, if you can, the last question can come from the room over here.
Hi, as a young person trying to get into astrophysics, I share your concern and I will be contacting my representatives. I had a question about the little helicopter. Did it just fly or was there something more than just flying around?
So it was, we'd never flown before, right? So it was demonstrating that we could control powered flight. We could tell it where to go. And it had cameras on it. And so for a while we were using it as sort of a scout where you can send it out to take images of something that would have taken us forever to drive to. And so at least you have some reconnaissance abilities. Something building off of that type of technology is Dragonfly, which is at least right now not canceled. It is supposed to move forward. And that is a quadcopter that's meant to go to Titan and perform actual experiments with a similar instrument to what's on the Curiosity rover. So a mass spec. It has a bunch of other instruments, of course, but again, biased about mass specs. Flying around Titan and exploring a world where the oceans are made of methane and ethane. So pretty incredible. If you want to talk about an alien world, that's it. So it flew around, it demonstrated flight, and then we used it as a scout for a little while. And it actually, finally, we were pushing it higher and further and faster because at the end it was like a technology demo. We wanted to see how far you could push it, and we finally crashed it.
Thanks.
Yeah, thanks.
All right, thank you, Dr. Williams.
Amy, thank you very much.
Thank you all so much. It's so wonderful to be here. Thank you. Feel free to reach out. I'm I think the only Amy Williams at the University of Florida, so I would love to hear from you.
All right, we have a official GAAC sweatshirt for you. If you would send me your size and an address to send it to.
Absolutely. There's like one day a year in Florida I can wear a sweatshirt, so that sounds amazing.
That'll change.
All right, thank you very much, folks. We're going to close the doors.
Thank you, Mike.
I don't want to close out.
Bye.
Thanks so much, Amy.
Bye-bye.
Good night, everybody. Thank you, Mike.
Night.
When you come to Boston, bring a winter coat.
Thank you, Michael.
Thank you all so
Bye.
much. Thanks, Eleanor.
Thanks, Dr. Williams.
Thank you, Alan. You all take care. Bye.
Well, that's.
Shit is really